So welcome back to our Q&A session. Today I will cover mainly UMTS, the third generation mobile communications system. UMTS basically was a compromise, as I explained. A compromise because some of the companies wanted to have a quick solution for the limitations of GSM. For example, in Japan or their second generation system, they didn't use GSM, so they needed a system with way more capacity. A compromise also when it comes to the details of the standard, and the core idea was, as I explained, to have one single standard across the world, but that was the kind of end of the story, that we had many different or several different competing standards. And in this lecture I mainly explained this UMTS comprising the old GSM architecture, GSM GPRS, plus a new radio interface. In other countries we had the CDMA 2000 technology using different core networks, and then there were some add-ons to the UMTS story, like the TDS CDMA coming from China and some other enhancements. So that was part of the story I told you. I told you also this crazy part of the licensing. So that was really a bizarre story, and I hope all the companies learned a lot out of this. What I also explained, and that's the interesting part, is this way of splitting up the architecture of the network, the user equipment, radio access network, and the core network. It's similar to the GSM architecture, and we will see basically the same when I talk about LTE. It looks more or less the same. The names are a bit different, but it's more or less the same. So UMTS, that's our third generation, and in this context, the first questions, and as always you can ask all the questions now related to UMTS, so don't hesitate. So the first question is basically what defines the third generation? So the initial idea, well, I already talked about this today, so but what defines this generation? And remember, we didn't have the idea of generations before, so no one talked about second generation when having a GSM. But what is speed requirements, transmission speeds? So that's exactly the point. So looking at this slide, there were certain requirements, IMT 2000. So the ITU said, okay, we want to have certain minimum data rates. The countryside, so it should be something like 300 whatever kilobit per second would be fine, and up to 2 megabit per second urban. So that was the capacity of a cell. So that was the idea. And you're absolutely right, also the multimedia support is important. Before that, think of GSM. GSM with 50 kilobit per second, multimedia, no way. So we have to have higher data rates. So that was definitely one of the main goals to support this multimedia. Because at these times, think of year 2000, we had more and more internet applications. We had the .com bubbles, all this. Then also what you wrote, spectral efficiency. So what does it mean? Spectral efficiency, in the end, we are from computer science. So for us, it's important to have many bit per second per hertz of the spectrum. And, well, we can also think of something like the space around us. So we want to squeeze as many bits per second through space using a certain amount of the spectrum. And we want to be very efficient. And GSM, well, it's an old technology, is not that efficient. So that's the core idea. Then I told you, I just showed you a minute ago, we had those different developments. So you should remember some of the reasons for this. Why didn't we come up with one single standard already? Today we have it with LTE, but at that time, why not having a single standard? Why going for these different standards, incompatible devices, different countries coming up with different standards? So what are the reasons? And there are many for them. Exactly, so pre-existing networks. So the point is, if you invested already billions in a network, in the core, you will go for whatever technology that can use exactly this core. So if you have this ISDN system, the digital phone network with this ISDN core, then you say, okay, this is basically a ISDN phone plus some extensions for the radio access. Not all countries had this ISDN. So for example, in the US, ISDN in the version we had it in Europe, for example, was not that dominating technology. So they did it in a different way. So they had different kinds of digital fixed phone networks. So that is one of the reasons. There are some other reasons, not only reasons based on technology. The strongest forces on the market, politics, so real politics from politicians, but also company politics and marketing. So if you already hold thousands of patents for one of the technology, you will fight for this technology, because then if this will be the dominating technology in the future, you know that everyone has to license the technology from you, and this will create a lot of money. And the politicians, they said, okay, we don't want to have the technology from this other whatever country or continent or etc. So that was really the fight going on this time. That was, I remember the EU Commission talking directly to the US Senate, and they had really a patent fight. And so that's one of the main reasons. So companies like Nokia, Ericsson, they wanted to enter the Japanese market. So they wanted to push their technology. So that's a problem. And then you're writing anti-monopoly laws. Indeed, there's also the idea, which is not wrong per se, to say we should not have one company basically making all the rules by creating the core components. So if you have different standards, you have at least some competition. The problem, however, is that the users will suffer by having incompatible phones. So today we really have this problem that in the end we have very few vendors of the core technology. So there is some competition, but to be honest, there are not that many really companies that manufacture the broadband modems for our smartphones. So indeed, regulations, law, politics, also technology. All this together led to these different developments. So, and I also pointed you to 3GPP. So if you find some time, just browse through the pages there. They have an enormous amount of information about releases, about what they do. And it's all open from the very, very beginning. And that's the interesting part, and that was new for industry and for this more or less government institution, that they say, okay, we create a standard, but this is open from the very beginning. So everyone can look into all the details, not only of the standard, but the meeting minutes, the discussions of all the groups. So if someone takes notices at the meetings, and they will be published on the FTP server in former times, and today you have these nicer interfaces, but you can look up all the old meetings, etc. So no one can say, oh, this was a secret whatever technology, so you could just look into it. Sometimes bizarre formats and sometimes huge Word documents and whatever, but you will find all the information. Okay, so now coming to the technology, I showed you a bit of the spectrum, and if you look at this, what was the focus of UMTS on in the early days? The focus also now, for example, let's concentrate on Europe, and how is this focus reflected in the spectrum? If you look at the spectrum and the use of UMTS and the spectrum, what do you see directly from the spectrum? This was not mandated by the ITU, but that was a decision here made in Europe. So one answer, underlying GSM specifications and development new UTRAN. That was the release 99, yes, but but what is reflected? So what was the focus? So indeed, yes, so it's based on GSM, but now if you look at the spectrum, you will find something specific. If you look closer, you see here a part and here a corresponding part. What is this? How are these bands called? It's used for duplex, it's FDD. So, and now think of applications. So what kind of applications fit perfectly to this setting? It's very, very simple. It's like, it's telephone. Exactly. Voice. So these are our paired bands. So in the early days of UMTS, uninterrupted voice, exactly. In the early days, UMTS, that was really a replacement for voice telephony. Although everyone said, hey, now we have the internet on our mobile phone, you see, looking at the paired bands, oh, it's paired. Okay, so paired, that means same spectrum for the uplink as you have for the downlink. So that's not the perfect setting for really this asymmetric internet traffic. But that's perfect for voice traffic. So today we use a lot of different coding and modulation, so we can have a way higher downlink data rate compared to the uplink, especially in LTE, where you will see this. Okay, so in the very first days, the first focus of UMTS was really on voice, and you see this in the paired band. I also talked about the usual conditions of the governments if you license a part of the spectrum, and the spectrum belongs to the people, because I mean this is like whatever, land, air, forest, whatever belongs to people of a country, of a nation. So if we license this exclusively to a company, we have certain conditions. And one of the conditions was coverage of the population in percent. So I said until end of December 2005, 50% of the population. Can you think of a problem of this formulation if you define coverage of population in percent? What happens if you tell a company, okay, you have to cover a certain percentage of the population? Exactly, only coverage in cities. That's a problem. The problem is the concentration in cities, and that is a big issue still today, because where do you make your money? It's in the cities. How can you cover a large percentage of the populations? It's in the cities. So maybe along highways, but the problem is that in the end you place your base stations first in the cities, and then maybe in suburbs, and then maybe in the countryside. So that was exactly a consequence out of this condition, coverage of population. And 50%, that's quite simple. Just pick the big cities like Berlin, like the Rhine-Ruhr region in Germany, like whatever big cities like Paris, etc. And then you have the coverage. But then you have many, many, many black holes or white spaces, however you want to call it, on the countryside where you cannot use your mobile phone. So that's a problem. And we will see with LTE that was different. So that here the authorities told the network operators, first you have to cover the countryside, or you have to cover a certain percentage of the country. So that is quite important, the difference of population and really coverage in a certain areas. And then we have the problem, what does coverage mean? I mean, still today, if you travel, for example, across Berlin, you have many, many spots where you do not have LTE, not 3G, only classical second generation edge network, and that's it, even downtown. So coverage of population, that really is a problem. So because what does it mean? Minimal coverage, voice communication, or coverage with high data rates? So coverage is it's not really clear. So you should say something that at least in whatever 90% of the area of a country, you should have at least something like 10 megabit per second, something like this. And still this is complicated. Rain, other users, etc., etc. And this is why today we have not only a catalog of these white spots where we do not have coverage, but also really people traveling around, performing the measurements and trying to place some more base stations, which then is a problem that many people don't like the base stations. And there are even people saying, oh, I don't need a base station, I've got a mobile phone. So, yes. Okay, so, but still today, LTE, we do not really have good full coverage. It's getting better and better, also due to the problem that you have to do more and more online. So, and this is one of the reasons right now during Corona times, it's not a big problem to convince people that we need this mobile communications. Okay, putting aside the problem of 5G and some bizarre opinions, but so that's was one of the problems in the early days of 3G, was only in big cities. Okay, and I guess we already covered the last question, so just to remind you, if you already have GSM, it's very simple to pick UMTS as third generation, and the same is true for CDMA 1 operators. They picked CDMA 2000, very simple reason. Why is anyone going for UMTS if you already operate GSM? Operators, yeah, most cost-effective upgrade path. That's always the point. So you pick a technology, the core is the same, exactly. So remember, the core is more or less, if I say the same, that does not mean it's exactly the same for each bit and all parts of the hardware. It just means you can reuse the major components. And that was the idea of adding this packet-oriented part to the GSM network. And so if you do this, then you can way more easy upgrade to UMTS. So exactly, and it's also a question of the licenses. So CDMA 1 operators, it was easier to migrate to CDMA 2000 in the US, as I told you, when we come to this kind of why do we have different systems or only one system on certain frequencies? I told you the difference that in Europe, usually the government says, okay, we license a part of the spectrum for a certain technology. And then the companies say, okay, we run now over this part of the spectrum, we run UMTS or we run LTE. In the US, the government just says, okay, this part of the spectrum can be used for this and that purpose. And then the companies can come up with different technical solutions. So that is the idea. The license themselves, as you write, are technology neutral. So indeed, the government, also here in Europe, the governments did not force anyone to use exactly this technology, to say, okay, you only get the license if you use this and that technology. But in Europe, it was always that the companies looked, okay, not only the migration path, but can we establish a completely different technology? And I remember that I think it was in Finland, there was a company that thought of using CDMA 2000 in the spectrum. They never succeeded. And this is not only that's not only a political whatever wish or something like this, but that's also a technological reason that you need the infrastructure, the core infrastructure, etc., etc. And to set up something completely new, that's a nightmare. So that's just if I say, okay, in Europe it's done this way, in the US it's done this way. This is rather, okay, this is the general mindset that it's done in different ways. And basically this is now over, as we all use the basically LTE. So the market decided for one system globally. And so this is then no real question anymore. So this is why now with LTE all these stories are over, I would say. Okay. So that was the introduction to the UMTS. You saw the story about this licensing, and I just put that into the slides because that was really a strange story. Then I covered more about the technology itself, but only the parts that are really completely different. The parts that are different from the other technologies. And what is different regarding other technologies is basically the CDMA part. So CDMA is really completely different, and this is something that did not exist before. Okay, I told you in the CDMA part you will see some specific parameters from the UMTS technology. So it is not that UMTS uses CDMA in a complete flexible way or in the same way as CDMA 2000 does. But as I explained, UMTS, there was the decision made, for example, that we have the so-called constant chipping rate. A constant chipping rate that has some consequences. So I explained the term chipping. I explained how you can create a certain spreading. So spreading of the data, applying these chips using this XOR. I explained the direct sequence spread spectrum. And in the context of UMTS, the CDMA is used, as I explained, to separate different data streams by spreading using orthogonal spreading codes. The orthogonal codes, they were generated by using this OVSF, orthogonal variable spreading factor coding, using these coding trees. So that was the one way of separation. And then we had the separation of the different devices using the scrambling code. And scrambling, that means you do not further spread your data, but you scramble it. So that's kind of, you mix it with a code without spreading, but to create more or less orthogonal codes. So more or less. So that's not precise orthogonal, it's just more or less orthogonal. So that was one of the key ideas. Furthermore, I explained the architecture, the UTRAN architecture, and once more, here in the architectures you don't have to know all the tiny details, but the key differences to the other architectures and why we have these differences. Okay, but we'll come back to this when we talk about the questions. So in UMTS you can have different data rates, high data rates, video, low data rates, signaling, something like this. And depending on the data rate, well, the data rate influences or is somehow correlated with the robustness. Because I showed you, depending on the data rate, because you have a constant chipping rate, you have different spreading factors. So lower data rates, higher spreading. Higher data rates, lower spreading. because in the end we have to come out with these 3.84 megachips per second. So that was the idea. But so what are the typical applications, and why do they fit to this effect of robustness versus data rates? So higher data rates, lower spreading, and lower spreading, that means lower robustness when it comes to interference, narrowband interference, and etc. So if you transmit, for example, video, in the end you don't need the robustness. So for video coding, that maybe you will drop some bits, you will lose some bits, that's not the problem. But for example, where you need high robustness is when you signal something. If you signal some information like call setup or so to control the network, you need a high robustness. But signaling usually uses only very few bits per second. And so it's a quite nice effect that if you have only very few kilobit per second, then you have to perform a big spreading, but that makes the whole transmission more robust. When it comes to narrowband interference, we learned spreading helps to mitigate narrowband interference. Okay, so then if we spread these low data rate streams, we make them more robust, and we need exactly this robustness, for example, for signaling traffic. We also have it for voice traffic. So the human ear, well, it's quite sensitive when it comes to voice, distortions in voice, dropped bits, but for video, it's not that big problem. So for the higher data rates, so you do not really need the robustness, and you don't have it in UMTS. So that fits together. So that's quite good that you have for high data rates the lower spreading factor. And that's all this table shows you, that you could use this, for example, for video. And then you have lower spreading, so not that robust compared to voice, or you could even have signaling. And signaling uses much less. This is the signaling channel, the control channel here, and so the spreading here can be way higher. Okay, so that is the basic idea there of, well, how to achieve this constant chipping rate. So depending on the data rate, you apply different spreading factors, and then the result is this constant chipping rate. I know this is really different from what we know in the other communication or GSM or whatever system, but that's the basic idea. We also see, because it's a CDMA system, we see near-far effects. So near-far, that was the problem when one station is very close and the other is far away. So how to counteract this? What is necessary in UMTS systems? What do they have to do? Measure and adapt transmission power. That's exactly the point. So if you look, for example, at this slide 82, you see there's a really more complex power control. 1500 times per second. I have to adjust the transmission power. So for systems like GSM, but also, as we will learn, for LTE, we have something like 200 times per second. And here we have 1500 times per second. So there's in each of these little slots, we have a command that's called transmit power control. And the transmit power control in both directions, tell the other side if they have to send stronger or weaker. So in the end, the base station, for example, tells 1500 times per second the mobile station send stronger or send with less output power. So you have to adapt. And the goal is always that all the signals should reach the base station with more or less the same power. That's the idea. And additionally, you should send with only the minimum required output power to minimize interference. So that also the base station should not send with arbitrary high power using your code, your specific code, because this will create too much interference for the others. So you always have to perform this power control to counteract this near-far effects. And that exactly is the problem, because doing this 1500 times per second, that really wastes a lot of power. And I remember in the early days when we didn't have the chipsets we have today, there was even in the mobile phones, there was a little warning telling you if you enable 3G, this will drain your battery faster. So it was recommended, if you don't need it, do not enable 3G. So it was really written there in the settings. Not today any longer, but that was one of the reasons. Furthermore, we had this OVSF, this strange, it's not strange, but we had this way of creating the spreading codes. Spreading can be done in many different ways, but in UMTS, we had this tree for the creation of the spreading codes. Can you imagine what is a problem if you do it this way? So you use a code and you concatenate the code with itself or the inverted code. That was the rule how to create this tree, and this is how we can go up to spreading factors, for example, of 512. But what is a problem? Can you imagine? Code blocking. So it's right, if you use, for example, this code for spreading, then you cannot use this part. If you use this part, then you cannot use the whole subtree. That's right. So you block, you have a limited number of streams. Exactly. So if you look at the example I just show here, you see, okay, we have one stream, that's one higher data rate, that's the second one with medium data rate, and then maybe a third one, or maybe number 3 and number 4, but that's it. A limited number of streams. Plus, and that's something you will see if we go back to this slide 83, you see that if you look at these numbers, what happens if you want to transmit 500 kilobit per second, for example? So what can you do if you want to transmit 500? If you pick spreading factor 8, this gives you 480. Exactly, you have to use 960. So that's the problem. So if you want to transmit 500 kilobit per second and you do not want to lose data, that means you have to go for 960, wasting a lot of bandwidth. Because if you use spreading factor of 4, remember this coding tree, none of the children of the subtrees can be used. So that really is a problem by using this OVSF version, because you could also think of a more variable system of creating codes, but more variable means more complicated. And this coding tree guarantees that you always create orthogonal codes. So that makes life much simpler. Without this, well, you have to calculate orthogonal codes, etc. Can be more complicated. So it's a simple scheme, but you might lose flexibility depending on the data rate you want to transmit. There's another option if you want to transmit a data rate of 500 kilobit per second, and you know that this includes forward error correction, so some redundancy. So you take your user data, put some redundancy to the user data. That's always necessary. What you can do is you drop in a random fashion bits and you squeeze it into 480, and you hope that your forward error correction then recalculates the original data. This is also done in your mobile phone. So you actually on purpose kill some of the bits. So you leave out some of the bits because you have anyhow forward error correction in your data stream. And then you can, well, accept a certain number of missing bits. Strange, but it works. Okay, so you see there are different ways of doing this, and sometimes you don't want to lose data for signaling, for example, and then, but this is done with high spreading, so you do not kill many subtrees. But for video, for example, well, there are certain limits. So you see there are certain problems using this coding tree. So the question is, do we need more forward error correction, higher bandwidth streams? It depends on the application. So that in the end, forward error correction, it's always a question how much redundancy you want to spend, and depending on the amount of redundancy, you can accept more or less bit errors and more or less so-called burst errors. Burst errors, that means many bit errors concatenated, so flipping bits in sequence. That's a burst error. And depending on the coding scheme, so forward error correction, there are many different ways you can do this. They can accept, for example, whatever 10% of the bits flipped, or they can accept burst errors to a certain maximum length, etc. So depending on the data rate of your stream and on the application, you need a certain amount of redundancy, something like 20% redundancy, 10%, 20%, 30% redundancy. We will learn in Bluetooth they send the same thing 3 times, so you have a lot of redundancy. So it depends on the application in the end. So if you have a certain stream, the question is 500 kilobit stream, that was my example, you have less usable bandwidth. Yeah, usually if you have something like, let's say, 350 kilobit per second, really user data, then you add forward error correction, then you might end up with, let's say, 510 kilobit per second. So in wireless systems, you add quite a lot. That's not just a bit, but quite a lot. For example, think of the classical voice transmission in GSM or the classical data transmission. We use something like 14 kilobit per second, but we learned that the single slot can offer you up to something like 23 kilobit per second. And a lot of the remaining bits per second is redundancy, forward error correction. So you add redundancy from 350 to 510, and then you can squeeze this into one of these 480 kilobit per second stream that is offered by the system. You cannot directly create 480 because you do not know where the errors occur, and this is then killing bits. You can do this in a random fashion so that it's not correlated. What you also do is you never transmit the bits in the same sequence as you create them to avoid the problems of bursty errors, because if a burst, so if an interference kills several bits in sequence, and this is the original sequence, this will really kill a lot of your original data. But if you mix your data completely, so if you shift it around, so like shuffling a deck of cards, so you shuffle your bits, and if you then have a burst error, the single killed bits, they belong to complete different parts of your data, and then you might be able to recover from it. But that now really goes into coding and coding theory. We never covered really this. But that's roughly the idea behind the story. Okay, so the user data rates are always way, way lower compared to what you have to transmit in wireless systems. So, but the next question, this should be quite clear now, how to separate different data streams from different users. So you should know where we apply the CDMA technology, not exactly how all the codes are created. But how do you separate? You should know the difference, how you separate different data streams and how you separate different users. So where you apply the CDMA. Which slide helps us here? Scrambling codes. So what do you separate by the scrambling codes? The users, exactly. So here the users slash the device. If there's a user or a machine, whatever, we don't care. But so the users, the device, that's a scrambling code. So the base stations have to know these codes. So the device and the base stations, they agree upon a scrambling code. And then the base station can talk using the scrambling code to a certain device. And inside the device, all the devices can use independently from each other the same way of creating the spreading. So this is exactly where they use this tree, and all the devices can use exactly the same. This is why you have, for example, the same spreading code here as you have it there. Without doing this, without the scrambling, all the devices had to talk to each other and, well, somehow synchronize in a way that they do not use the same spreading codes. That's way too complicated. So this is why all the UMTS devices use the same spreading codes, if necessary, and then in addition we apply the scrambling. So that's the point. So already at this point we have our 3.84 megachips per second already at this point. So the scrambling itself doesn't do anything here, so it does not further spread. So that's basically the idea here. So CDMA used 2 times. One time to separate the data streams and one time to separate the different users. Okay, now finally, if you look at the architecture, if you compare it, so do you see really big differences? Are there major differences? Is it basically the same? Where are the differences and why do we need the differences? And you're fully right. The major difference is you can forward data between the radio network controllers without the core network knowing. So that was exactly the point that, for example, if you assume you use equipment 3 goes from the upper cell to the lower cell, then you can forward the data stream here and you might still be able to receive data here. You merge the data and you forward the data to the core. Or also the other way around, you can split the data and you can transmit at the same time the data via 2 different antennas to a single mobile station here called user equipment. So not MS anymore, but UE, but that's basically the same. Because we use the same frequencies anyhow. So it's the same. So that is That is the basic idea. Okay, so that's the core idea. I will come back to the other question in a second. That's one of the core ideas of UMTS, that you can send data streams via different antennas to perform something we'll cover in a minute, soft handovers. But for the core network, you see, there is not really a big difference. If you look at slides like 88, you see here now a GSM component and a UMTS, a BSS from GSM and a RNS from UMTS. So there is no difference in the core network. You should be able to identify the components on a certain level. So to say, okay, this is our packet switched part. Up here we have our circuit switched part. So this goes to the classical ISDN fixed network. This goes, for example, to the internet. That's the idea. And then we have some additional databases. But as you see, that's more or less the same, no matter if you then use the UMTS or if you use GSM. And that was the idea of saving a lot of money, because you could more or less keep the infrastructure. And you also see that the interfaces here are more or less the same. So the network, if I go back to the other slide, the network in the core will not notice anything from these new features of UMTS, that now you can send data via different streams. So it's not possible to say, okay, we forward the data directly in parallel here. So something like this. So that we say, okay, we transmit it via two different RNCs directly to the core via two, let's say, two interfaces. That doesn't work. So the system doesn't like this, so you have to go via this RNC. That's the point. So otherwise you have to change the core network. Again, that's more expensive. So this is why the system stayed in a way that says, okay, we do not really touch the core network, but we change here inside the radio network the way how you handle the different streams. So that is the idea. Okay, now let's come back to one of the questions. Why do we need scrambling and spreading separately? Does one device really have several data streams at once? And what is an example? So if we go back, let's say, to this slide, you might think of a device that uses video and or you calling someone, you talking, at the same time you download emails. These are two different data streams. In UMTS, voice is later mapped. So voice data stream is mapped on circuit switch data. And then if you download email with whatever data rate, this is then, it's maybe here, this is then mapped to packet switched. So that's complete different data stream. So if you talk to someone and you're sending messages at the same time, that's two data streams. Additionally, for each of the user data stream, this is, well, I never went into all these acronyms, a dedicated physical data channel and a dedicated physical control channel. For all user data stream, you always also have a control stream that controls the data stream. So basically the signaling for the data stream. So you always have user data plus control data. So you have many different data streams at the same time. If you look close, I never wanted to go into all these details, To your control channel, the so-called pilots belong, and this power control thing. So all the control information, like power control, that belongs to this control channel. And all data belongs to the data channel. So you automatically have, if you have a data channel, an associated control channel. So you send data, and then in addition, some bits that control this data channel when it comes to transmit power, etc. So you always have a dedicated physical control channel in addition. So you can have different data streams at the same time transmitted over the system. So that works. Okay. So now we have covered most of the questions, and the remaining part of UMTS, I mainly, from a technical perspective, I covered the handover. So we had different ways of handover. I think it's something like 36 different types of handover, standardized handovers to satellite, and from 3G to 2G and 2G to 3G. I also mentioned that most operators do not support the handover from 2G to 3G. So during a connection, but they all offer 3G to 2G, so kind of a fallback if there's not enough coverage in the UMTS network. I also showed you the start of all of this, and then some of the enhancements of GSM, things you might not even remember, but the mobile phones, they still know how to handle MMS, EMS, these things. All the mobile phones know how to handle new modulation schemes like Edge. So that's 8 PSK instead of this Gaussian minimum shift keying. And this is how we can reach high data rates. And that was the reason why Edge was not introduced before the rollout of UMTS, because this was really a threat to UMTS. If you say, hey, without any investment, we can do Edge, and then we have basically the same data rates we had initially for UMTS, not what we have today for UMTS. So that was the story about Edge. And then I also briefly touched the new versions of UMTS. So all the mobile phones, if you see a little H+, they use this evolved high-speed uplink packet access and downlink packet access. So in general, with the new releases, you see here release 7, 8, 9, we can have several tenths of megabits per second as real user data rate in UMTS. There are some releases that, for example, say, okay, if we use 2 or more carriers, so if we have more carriers, then we can offer more and more, but that's sometimes only in theory, because you have to have several carriers available. And so if available, then you could go up to, and you see these data rates are quite high. So that's a lot. That's UMTS, so not LTE. Starting from release 8, we see also LTE, but this will be covered in the next session. So you see there was quite some enhancement in UMTS, but I doubt that you will see much more here. There can be here and there some enhancements, but some of the operators already said when they will actually then shut down the networks again. But I guess they will stay for a while. Okay, now some final questions. If we look at the handovers, so why is GSM a hard handover, and why is UMTS a soft handover? What is hard and what is soft in this context? Okay, hard handover, radio links are broken and re-established. Exactly. So for hard handover, there's really a point in time when the mobile device has to switch to a different frequency and to a different time slot. So remember, in GSM we have channels, different channels, and then if you operate on one channel and you have your TDMA frames, so you have the frequency here and time there, then within a TDMA frame on a certain frequency you have a time slot, and then the handover means you have to jump on a different channel, so different frequency, but maybe also in a different time slot, depending on the availability. And there's a certain point in time where you really break with one of the networks and you jump into the other network. Everything is prepared, you know where to jump to, etc. But you have to do this, and you have to re-establish everything in the new cell. So that's the hard handover. The soft one is different. So for the soft handover, connection to multiple base stations is active all the times. Yes. So you all stay in the same frequency. Again, if we have the frequency over time, you have wider bands. Yes, that's CDMA. So you have a wide band. And all the antennas, they use the same frequency. So there is no jumping in frequencies. So yes, there are different carriers. So the operators might have different carriers. But usually you stay in the same frequency. You stay there. And then it's like rather like multipath propagation. So you have different paths caused by reflections on buildings or by a different antenna or by several different antennas. So you will be able to receive, let's say, automatically, let's say the 5 strongest paths. So you could imagine you have 5 paths and then a delay component, as I explained in the very beginning. So different paths, and you receive your signal and you basically combine them after delaying. And if the signal you receive is from a different antenna, or if this is a reflected one, well, that's not really the important part. So, and this enables a soft handover, so there's no hard switching. Internally, yes, you have to set up a path via maybe a new RNC, via a new eNode B. So internally you have to do something, but for the mobile station or the user equipment itself, you will not really notice this. Now if you compare the handovers, now look at the core. What does the core notice from the handovers and from the types of handover? Does the core notice something? And if yes, what or what not? Now looking at the classical UMTS architecture. Does the core notice something? Soft handovers, hard handovers? Does the core notice anything at all? No interruption? Well, depending on what type of handover. So does the core notice a handover at all? Well, it depends. So the core notices switches of the main RNC. Right, so it depends on the type of handover if the core notices something. So for example, if you perform a handover within eNode B, the core itself, the core starts here, that's our core network, will not notice. So that's handled internally. If you switch between 2 eNode Bs, so that's our second one, well, that's handled somewhere here internally. The core will not notice anything. If you switch between 2 radio network controllers, soft handover, then this is handled again internally. And you see, the core will not notice as long as you stay with the same RNC. The core will not notice. the core will notice as soon as you say, okay, now we completely switch over to the second RNC, then the core will notice the handover here. Then the core has to be involved. Before that, it doesn't matter. And that's a hard handover for the core. So for the core, that's a hard handover, not for the user equipment, but for the core. So the core notices a hard handover if you have to hand over between two different interfaces. And definitely the core notices if you hand over from 3G to a 2G system, depending on where you're attached to. So that's a different interface. But so the core does not notice anything in the context of soft handovers. So because, well, this is handled inside the UTRAN, inside the radio access network. The radio access network handles this soft handover, and that's it. So then the core will not notice. That's the idea here. Okay. So now we have some more questions. So consequences introducing packet-based transmission. So if we have more and more packet-based transmission, there are several consequences you may think of. If we have packet-based and not, well, packet-based transmission in general, we have several consequences that makes life, let's say, simpler. What can you think of? What happened? We introduced IP and packet-based transmission to our mobile phone networks. What are consequences? Several consequences. You can use internet services, and what is the consequence there if you use internet services? Think of how to make money. More data load. You don't need additional services by the mobile providers. That's right. The question of interruption, can data packet streams or packets be interrupted more easily? We don't have a stream. It depends. The internet itself operates on a best effort way. So yes, packets, we can lose packets, we may lose packets, but that's what happens in the internet as well. So that can happen. That's a question of the higher layer protocols. So the main problem, well, not problem, but the main point is, as soon as you introduce IP-based packet transmission, the mobile phone network is nothing but a big bit pipe. And the services can be created at the end, which is the nice thing from an internet perspective. But why having special services like MMS or EMS or whatever? You just do your IP-based messaging. So as soon as you have higher data rates, you can do a lot more at the end in the apps. You do not need the network support any longer. So, and this means, well, the operators do not make that much money. You saw the examples SMS and successes of SMS. There were some ideas, but they were never successful because we all had whatever WhatsApp and Telegram and all the messenger services. So the point there is basically by introducing packet services, they killed their revenues on their own. Today, but that's a different story, the operators try to introduce software-defined networking with certain quality of services for specific services. Then you can make some money out of special types of networks. I will come back to this in the Outlook. So why do we still have MMS? Yeah, it's a good question. It costs quite a lot. But there's still a case that MMS can be understood by all the mobile phones, and there might be some services where you still might need them. I can't remember when I last used it. So why it's still available. So basically, no one touches the running code. So if you have a service there, it could be that there's some service relying on this, and then it's still there. So for SMS, I know some applications that need the SMS because that's a way of how to reach mobile phone. WAP and MMS is also still available on the mobile phones, at least as far as I know, on most of the mobile phones, but not really used that much anymore. There are some services that can use this. So the point is, as you point out right way, you can evolve the protocols and the feature set faster than you can upgrade the network. That's exactly also one of the problems, that as soon as you have this, let's say, network agnostic IP, because IP doesn't care, it's just best effort, so it just tries to transfer packets, then you can put whatever you like on top, and suddenly you notice, oops, it doesn't work. So one just recent example is, we all switched over to video conferencing due to Corona, and then many of you also noticed, well, it's shaky a bit depending on the network. And a real problem is, for example, wireless LANs together with video conferencing. Suddenly you notice, although you have high data rates, it's shaky because latency, packet error rates, etc. compared to fixed networks. So having a high data rate, having IP connectivity does not mean that you can suddenly use all different types of applications. Think of autonomous cars. This is one of the reasons we want to have the 5G networks, because although we have gigabits per second on LTE, we have too high delays in the network, so we cannot really remote control a car or something for this, for example. So that's a problem, that you can suddenly use all applications you're used to from the internet on a network that was never made for it. So that's one of the problems. Second question, doesn't that also mean that messing around with BGP can disable the phone system? Well, no, not really. So, well, if you mess with the routing inside the phone system, then yes, then you could, create problems. But usually all you see is the IP address, a netted address, so network address translation. So inside the network, typically you use a private address. There are also some operators offering public IP addresses, so global addresses. But you see an IP address, and you have an access point. And the access point is a router. And internally, inside the network, you have these serving gateways, which are routers, so GPRS, and they handle the packet traffic, and you cannot influence the internal routing. So the BGP protocol, that is an inter-domain routing protocol. That means routing between so-called autonomous systems. So you route the traffic between those huge systems. And the mobile phone network of a certain operator is a separate autonomous system, and you do not have any control of the internal components. So outside, independent of mobile communication systems, you can mess up BGP. Yes, because the classical BGP is not protected. That's where we have a lot of work, publications, projects, how to protect BGP, how to make this more secure. There are versions of how you can secure the BGP. So BGP is the Border Gateway Protocol. That's the protocol that handles the routing between huge components. So routing, okay, you meant between different operators. Not sure if emergency call numbers are on my network, for example. So emergency, that's a completely separate topic. So emergency calls are handled inside the network. Also, if you do, for example, voice over LTE, which is a pure IP-based system, no more circuit switching, but I will come back to this next week. So then you have internal databases that have to map your current location to the next emergency control center. So emergency call if these numbers are handled in a complete different way. So this is a mapping. It's a mapping of database, and the network operator is responsible for this. So there are some more of these special services. And all the other routing, it's just a question internally. So the gateway does the netting, so the address translation. Your packet reaches the gateway, and then you perform internally whatever routing. So the operator could use OSPF as an intra-domain routing system to route the packet to the gateway closest to you, and then it's forwarded to your mobile phone. And, well, as I said, emergency, that's completely different. Paying for incoming MMS, you cannot reject it. I don't know if you cannot switch off MMS at all. To be honest, I haven't received an MMS for, I don't know, years. So I'm not sure, depending on the operator, why you have to pay for something. I also know that at least in former times in the US, you had to pay for incoming calls on your mobile phone number, because the argument was the person calling you does not necessarily know that this is now a mobile phone number and you're traveling somewhere in strange countries. So you have to pay for any additional fees. So there were some very strange combinations why in former times people didn't want to reveal their mobile phone numbers. I hope this is over. Although this is tariffs and pricing, that's really different from technology. That's something completely strange, I would say. Okay, so two more questions. So higher data rates in UMTS. Yes, I showed you that in UMTS we can go up to 500-600 megabits per second. What are the reasons? Why can we have higher data rates now in UMTS? We started with maximum 2 megabit and now we're up to 672 megabit per second. What do we do? There are different things we can do. And some techniques you know by now, what we can do to achieve higher data rates. What can we do? Just give me some keywords. How can we achieve higher data rates? We want to squeeze more bits per second through, well, a certain space. What can we do? What do we have to change to make it faster? Many different answers. Different chipping. You could change the chipping. Well, usually that requires a lot of changing of the technology, but you could change indeed something with the chipping, with the coding at that point. But very simple. Just go back. Exactly, different modulation. Go back one slide. You see the higher data rates, they now use, for example, different modulation. QPSK, maybe you remember, that was the scheme that had these 4 points, quadrature phase shift keying in the constellation diagram. So you could code, just a simple example, 2 bits. No matter how you do it, just an example. Now, instead of having 4 points, you could go for 16. So you squeeze in more, now more in this. So we have 8, so we squeeze in even more. So that's a 16 QAM. And now we can code whatever, 4 bits into 1 point in the constellation. So modulation, different modulation is one thing. And the next thing that's hidden in this, where do we have it? Here, for example. So we change modulation. We now go for 64 QAM, so even more, plus MIMO. We use 2 by 2, so 4 antennas. We use more antennas. So as we learned in the context of MIMO, we can separate, for example, the data stream and send lower data streams, so a quarter of the original data stream over each of the antennas. That's one of the ways of doing it. So MIMO, we can achieve higher data rates. And then the third point is, that's down here in the last line, carrier aggregation. We can use more spectrum. Sure, if you use more spectrum, you can send more bits per second over the spectrum. Double the spectrum, you immediately have double the data rate. So spectrum plus modulation plus MIMO technology, this all together, well, allows us to transmit more bits per second over the air. Okay, so data rate increases, great. The delay, that's the problem, remains the same. 100, 150 millisecond from the mobile station to the base station. So what problems do we have if we now use, for example, we have the fast connection, so we have megabits per second, and now we use something like TCP. What problems may occur? For those of you who know a bit about TCP, congestion avoidance, round-trip times. And that's also a forward pointer to one of the last chapters where I will cover TCP. Data loss, that's a problem. Indeed, that's one of the problems, because the reaction of TCP is, TCP, Transmission Control Protocol, is a reliable layer 4 protocol. If you lose data, TCP retransmits. And but that's something, yes, we have to do because it's reliable. Congestion, if we have congestion, then TCP reacts. The problem is TCP checks the round trip time. How long does it take for my packet until it's acknowledged? And the setting of the round trip time now, that depends on the delay. And the delay of your data traveling from your device to a server, for example. Over the fixed networks, that's some milliseconds. Over the mobile networks, we suddenly have these additional 100, 150 milliseconds. So in the end, we have at least something like 150 milliseconds this way, 150 milliseconds that way. And as you will learn in the last chapter, the maximum achievable data rate using a protocol like TCP only depends on the round trip time and the bit error rate, and not on the data rate of the lower layers. Why? I will explain. So the problem, so this is why this is a forward pointer, the problem is if you use protocols like TCP, they are not well adapted to these effects of mobile communication, wireless communications, that you have high round-trip times due to forward error correction, scheduling of packets, etc., etc. So in the end, although you might offer something like 600 megabit per second, you can never use them if you use protocols like TCP. That's a problem here. This whole problem, I will come back in the chapter about internet protocols. So this is why I said forward pointer. Maybe you remember when I cover this. Exactly, because we still have this high delay from the mobile station to the base station. TCP does not perform that good. This is why we have certain adaptations of TCP, especially for wireless domains. But that's also one of the reasons why in LTE we will bring this down to something like 10 milliseconds and even below. There is something called today, but that's really current technology, so-called ultra-reliable low-latency communications. And that's something you will see in 5G networks. Ultra reliable and low latency. But that's very difficult to achieve. So, just to show you, okay, there's something more I will explain, and there are some more problems. We also still fight today in those mobile phone systems. So the story is not over there. So because delay is a problem. So what you should remember is high data rates are fine, but that's not the complete answer to the problems we have today with our applications. We also need low delays. And UMTS, GSM not at all, but UMTS is not the perfect solution there. And this is one of the reasons why UMTS, and there are some more reasons, is not the technology of the future. It's there, it's widespread in use, but basically it's past its peak. So it's now more and more replaced by LTE. So you will understand the whole question way better when we cover the TCP later. Okay, so some more questions from your side. You see sometimes Wi-Fi calls on your mobile phone. What is it? Why do you see it sometimes? So the point is that more and more, depending on your operator, the operators try to offload calls, if possible, from the mobile phone network to your wireless LAN, your Wi-Fi network, or wherever you are. So because Wi-Fi networks, there is capacity, and you do not waste the capacity from the mobile phone network, and then it's possible to use the Wi-Fi networks, if available, for phone calls. But that requires a mobile phone that supports it, that requires a network operator that supports it, and in the end, it's all voice over IP. So what we use today with the new phones and the new networks is voice over IP, and then it doesn't matter if the system says, okay, it is already an IP packet, then I route it over the wireless LAN network. If not available, then over the LTE network. So you can use several networks even simultaneously. So what the phones can do is they can split up the traffic stream and using different network technologies, and then you will bring back at the mobile phone the different traffic streams so that you see a single traffic stream for your application. So you have different paths for your data. And if one technology breaks down, so you're out of coverage of wireless LAN, then LTE takes over. And as soon as wireless LAN is available, then you can use it. There is even the term LTE assisted use of wireless LANs, so that the LTE system can use, that's in the standard, can use also unlicensed spectrum. So that means that depending on the availability, the LTE system is aware of, for example, capacity in the wireless LAN spectrum, and you can use it. So there are different technologies that can make use at the same time of different carriers, as they are called. So LTE is one of the carriers, but you can also use anything else because it's an IP packet anyway. And as long as the network technology is fast enough, you will not notice it that much. Well, there is some delay. So Wi-Fi calls, it depends on the operator. And you will not notice, it's just the mobile phone that will, together with the operator, will pick the appropriate network. Okay, so some more questions from your side. So we covered now the classical second and third generation, and as I said, the next time then we focus on the fourth generation. So please do have a look at the material I provided for LTE. That's not that much, but it covers again key characteristics that are different from the existing systems. So I will not explain again the complete system, but mainly the differences that you see. Okay, that's one of the differences. And that's something you should remember, the differences, not to repeat the complete architecture or whatever. That's way too much anyway. Okay, I guess time's up anyhow. So thanks for today. And as always, if you have some more questions, send me a mail or ask next time. And then we read each other next week. Okay, so have a nice week. Thanks a lot.